This is experiment M6. So in this one we are oscillating loaded spiral spring. So our question goes like this: is all our questions from I to S, I. So like previously we've set up our experiments of taking the pointer reading 1. Our L1 is when no mass is attached to the spring balance, and you get it when you put your scale pan and you put your pin, you measure it. Before now you've placed your ruler, and the point where the ruler is showing, assuming the point where your ruler is showing is 41 and where this one is showing is 53. So when you subtract it, your L1 is what you get when you subtract that 53 from your 41, and that's what you'll keep because you use it and get your extension and every other thing. Then now the other one is to include a mass of 50 grams. When you include a mass of 50 grams to the spring balance, you're going to take the reading for each of them and repeat them for 100, 150. And remember, when you're taking the reading for each of them, you're subtracting each reading from the initial length, and that's what you're going to record. So you're going to take every one of them, and after doing it, it's going to give you your table of value. So this is my table of value. This is my table. Your load stroke mass measured in gram, your L2, your extension is that L2 minus that L1 we got with no mass attached. Then your time, your period, and t squared. So this is how my graph looks like. It may not be exactly as yours, but this is mine. Then the next question says you should draw a best fit straight line through origin. This word is key. Origin is your 0 with load, like with your load, your L as your abscissa. Your abscissa is your X axis, like the horizontal axis. And extension, this is your extension. Your extension as the ordinate. The ordinate is your Y axis, the vertical axis. So you're going to draw a line of best fit, right? So this is how my graph looks like. So you write a graph of E against L. So this is how my graph looks like right now. So now from your table of values you have your starting from this place, draw a best fit straight line through origin with load as abscissa. So this is your load, this is what you're going to use, and then this is your extension. So you're going to read it. So the list number here is 0.4, right? And then 1, 2, 4, 6, 7. So you're going to read this thing. You're going to read in. You'll just read in 1, 2, 3, 4. All of them till 2 cm. Then this one, you read it in 15 for the x-axis. So now we have load. That's our x-axis, 2 cm to 50 grams. And then your extension 2 cm to 1 cm. So this one is the simplest one. So when you check your extension 0.4, your load is 50 grams. So if you come here, 0.4 is very easy to count, right? So this is 0.1, 0.2, 0.3, 0.4. So 50 grams is to 0.4. So that's the same thing you will do for every other one. 100 is to 1. So your 100 grams is to 1, your 100 grams is to 1. So when you are done, the question says you should draw a best fit straight line through your origin, and your origin is 0. So our point and our target is to make sure that whatever line you're drawing here is going to cross through your origin. See your origin, your 0. So now we have 6 points. If you try to join this thing, this is going to cut through this place. Like, it's not going to give you the best of what you want, and it's not going to meet your requirements of it cutting across your origin. So the best thing to do is to split your points into 2. So we have 3 up and 3 down. So you make sure that your line is not going to touch any of the points, and cut it in a way that it goes through your origin and divide your points into 2. So I have 3 down and 3 up. Then you find your slope, and when finding your slope, connect it to the lines that you can easily read. So now we have change in A over change in L, your extension over your load. So now this your change in A is going to be, this is your 5.5, and then this one is, if you're going to read it, it's going to be 0.8. Then your change in L we have 350. So this is what you're going to use and get your slope. So when you're done, the next question says you should calculate your spring constant, and your spring constant is slope equal to 1 over k. K is your spring constant. You're going to get your k, you're going to do inverse of slope, that's 1 over slope, and our slope is 0.0188, so we're going to do 1 over 0.0188 and get our answer. Then after that, the next question says you should plot another graph with t square as the ordinate, that's the y-axis, against the abscissa. Find out the effective mass by taking the point of intercept of the resulting lines on m-axis. So your intercept is going to cross through your m-axis, not the origin like the previous one. So the question said you should use t square, right? So we are plotting another graph. So we have t square here as our ordinate, and then we have m, that's our mass, as our abscissa. From the same table of values, you find what your mass is and what your t square is. So the least number here is 0.05, 0.07. So we are going to be using 0.05, and your mass is still 50, 100, 150. So we put our 0.050, 0.100, 0.150 for the t square. So when we come to this place, you put our 50, 100, 150, 200. So what you're going to do now is this: when you are done putting your numbers, if you want to know the particular number to put, what you should do is just check the list number there and check the progression. Just like in this list now, we have 0.07 and the progression goes like this. So if you use it anyhow, like, it's not going to work, but you need a progressive number. So if you do 0.05, the next one will be 0.100. So all these numbers are still within what you are doing. So what you will do now is this: the first number is 50, right, against 0.0795. So to learn how to read each of these lines is very important. So I've told you, if you're using 0.050, divide 0.050 by 10, because all these tiny lines are 10 in number. When you divide it by 10, each of the line is 0.005, each of this tiny line. So when you keep on adding 0.005 to your number, it will help you when you get to something similar. You're right. So this one now, this place I put my point is 0.08, because if you check here, I'm having 0.0795, but there's no how I'm going to get 0.0795, so I approximated to 0.08. So that was why I'm having something around this side. So that's what you're going to do till you are done with placing of your points. Then the next question says you should find out the effective mass by taking the point of intercept of the resulting lines. So you're going to draw your line in such a way that it's going to cut through your m-axis, that's your x-axis. So we have 6 points here. So what we're going to do is we're going to place our ruler and make sure that it does not touch any of the points, but it's going to split the points into 2 and then cross through the m-axis. Remember, this one is through the m-axis, so I try to split my intercept cuts across 50. That's where my intercept cuts across. Then the next question says we should find out the effective mass by taking the point of intercept of the resulting lines. So my effective mass is 50, because that's where my intercept cuts across. Then the next question says, which graph in this experiment represents Hooke's law? Mention how. So in this particular graph, in this particular question, we have 2 graphs. This one, a graph of E against L, and this one goes through the origin, and then a graph of T square against M, and this one cuts through the M axis, that's the S axis. So it's asking which of these experiments represent Hooke's law, and Hooke's law is that force is directly proportional to extension, or load is directly proportional to S. S is mass here. So if you check the graph that goes through the origin is the experiment that goes through the origin is the graph of E against L, because that's the one that cuts through the origin. Because the graph passes through the origin, it is a straight line graph here. As you can, even in as much as we didn't cross it in any of the points, but it's a straight line graph. And then it shows that extension is directly proportional to the applied load. So it's directly proportional because it starts from the origin. Here, Hooke's law is being obeyed. Then the next one is, why did the graph of c squared as a function of m not pass through the origin, right? So why did this particular graph, the graph of t squared against m, not pass through the origin? And our answer is the graph of t squared against m did not pass through the origin because there are energy losses due to air resistance and internal damping. So the internal damping prevented it from, that's the friction prevented it from passing through the origin, and there may be zero error in the time measurement. So there may be error in the calculation. That was why it didn't pass through the origin, rather it cuts across the m axis, that's s axis. Then when does the mass, we are in SII, when does the mass spring system attain I, the maximum kinetic energy, II, the maximum potential energy during vibration? How does the total energy of the mass spring system vary during free vibration? So in answering this thing, you have to check the keywords that has been given to you. So this one is, when does the mass spring system attain I, the maximum kinetic energy? So now, for maximum kinetic energy, we attain it when we are at the mean equilibrium position. When we are at the equilibrium position, then when extension is maximum and when velocity is maximum, that's when we attain maximum kinetic energy. You know, kinetic energy is energy in motion. So when your extension is at the maximum and when your velocity is at the maximum, then you know it's kinetic energy that is being attained. Then this one, the maximum potential energy during vibration. Potential energy is that energy at rest, right? So when is potential energy maximum? Potential energy is maximum at the extreme position. Like when you draw your pendulum, if you're going to use a pendulum, when you draw your pendulum, potential energy is at the extreme positions. Is at the extreme position while your extension is maximum and your velocity is zero at potential energy. Then the next question, how does the total energy of the mass spring vary during free vibration? So during your free vibration, the total energy remains constant during free vibration because it's a free vibration, so the energy remains constant. Energy continuously changes between kinetic and potential form, so the energy changes. So all these things is something you can browse and get answers to them. State 2 precaution taken to obtain accurate results. So you can browse what are the 2 precautions you take during when you're oscillating a loaded spiral spring. All the readings you're taking at eye level to avoid parallax error. When measuring the length or extension, you know that pin, so you try as much as possible to take your reading at eye level to avoid parallax error. Then the load was gently added to avoid overstretching of the spring and ensure that you read your extension accurately. So you can just form up something and browse about it. So I hope you enjoyed yourself. Don't forget to like, comment, and subscribe. Thank you so much.